perception and investment prejudice within the UK. So we really want to spread the word, and it's amazing when I'm talking to people how they still think there's no commercial activity going on around graphene. So we want to change those views, and we'll move that forward to this evening, hopefully. So we're going to go through who we are. We'll give an introduction of myself. Adrian will be talking through graphene and the 2D materials science and the manufacture, and I'll be talking about the commercial applications. And obviously not all the commercial applications, and hopefully through the Q&A we can talk about other opportunities and the things that are happening in the graphene environment currently, which is really exciting. It's moving forward at such a pace that it's difficult to keep up with where it is. So I think hopefully you'll be pleasantly surprised. So Adrian.
Yeah, well, this is what Mike and I look when we wear some ties. This was us in DC just over a year or so ago. I'm CEO of Nixene Publishing, editor of Nixene Journal, and I'm a chemist originally, so industrial chemist. By examination to the Royal Society of Chemistry, I've had a proper job and worked in industry, worn a white coat, invented things and done all sorts. I'm also a board member of the International Space Elevator Consortium, so maybe take some questions about that. I'm an advisory board member of the National Graphene Association in the USA as well. So I play around with lots of things from different angles. That's a very sort of a brief headline, lots more detail, which we'll talk about later. And Mike, over to you.
Yeah, I'm Mike Maddock. I'm a visiting professor at the University of Sheffield, and as Steve said earlier, I am the managing director and co-owner of Performance Engineers Solutions Limited, which I'll give you a brief overview later, based on the Advanced Manufacturing Park in Sheffield. And the link between Adrian and I is we work very closely through the two companies. Also, we have set up another business for a collaborative project that we're moving forward. So we've been working very closely over the last 2.5 to 3 years. So apart from the visiting professor, I'm also a regional and national board member of IMechE UK, so representing the manufacturing area, and through that I sit on the Net Zero Advisory Commission for the government and IMechE UK, heading towards COP26 and looking at how we can make improvements in net zero and carbon neutral technologies through manufacturing. And I also sit on the Innovation Advisory Board for the government as well, talking about innovation and the next strategies for the future. So very briefly, some of you will already know, but Performance Engineered Solutions Limited, as I say, based on the Advanced Manufacturing Park in Sheffield, which I would call our Kensington address, and the Global Centre of Advanced Manufacturing, which some maybe disagree, but at least you can't answer back currently. Our business is a high performance engineering business and a consultative business. We work across multiple sectors. We're a multidisciplinary team. And we've been in existence for over 10 years. One of the reasons to be based on the Advanced Manufacturing Park, we work very closely with the catapults, which are, for people outside of the UK, are basically government-led research establishments to unlock technology in different sectors, which is really interesting. So, as I say, we deliver right across the board. Unfortunately, over 90% of our work is under non-disclosure, so we can't tell you who we're working with and what we're working on. But give you an idea, there's something here on the left-hand side. You see this aircraft. That was something quite exciting we worked on. It's a CDART 1952 Delta Wing aircraft that we were asked to scan, reduce in size, and then use composite Kevlar titanium and made it into a 1/3 scale aircraft. Not a radio control, but it's actually flyable. With all the control systems, and it's flown by an animatronic pilot. So actually you control the pilot, not the aircraft. So it's almost an analog defense system, which has been really interesting and really enjoyed building on that. But we're right across the board. But that'll give you an idea. And I think our key approach is, because we have a real holistic view of markets and technology, that we cross-pollinate technologies across multiple sectors. And when we work closely with our clients, we're really collaborative, and we class our clients as partners more than anything else, but we are a really strong consortium. We've frozen up. Can you still hear me, Adrian?
I certainly can, Mike. I can see the mouse moving, but not the slide.
Yeah, it's frozen up. Give me a second.
Well, I'll start talking to the next slide anyway while you're on there. Yep. We set up Nixene Publishing a few years ago, and we're based at the Graphene Engineering Innovation Centre, the GEIC, in Manchester. Now, some of you in the audience will be graphene experts, and some of you might be aware of it from more of a distance. The GEIC is one of 3 major centres on the University of Manchester campus. There's the National Graphene Institute, the Royce, which is probably opening shortly later on this year, and the Graphene Engineering Innovation Centre. This opened up in 2018. So this is where some of the world's leading scientists and engineers work and play with graphene. When we're not in lockdown, you'll usually find us on the top floor in that building. And in there is basically a lot of the future is happening for graphene in all the labs. So we're based in this part of this ecosystem. So we get to talk to a lot of the industry people, a lot of the academics, not just in the UK, but our reach is worldwide. We've also got a base in the States as well. So we're branching both sides of the Atlantic, but we cover the world in our reach and what we're looking to be happening with graphene in 2D. So next slide, please, Mike. It's great. As Mike said, the pace of change of graphene is absolutely astonishing. Now, some of you will have a range of ways of approaching this stuff. You'll all have an interest in graphene. Some might think it's old hat, nothing new happening. Others might have heard bits and pieces. Maybe some of you heard Stephen Fry talking about graphene just before Christmas on his review of 21st Century First. So the point I want to get across is whatever you've heard about graphene is probably out of date already. The pace is moving that fast. We're on this full time and we're working flat out, just keeping up to speed with what's going on. And when we first started getting interested in graphene about 5 years ago, then we looked around for a reliable source of information. We couldn't find anything. It was either biased, incomplete, or we just didn't trust the source. So we ended up defining and building our own information source, which eventually became the journal. So we built the company around that. And the journal was officially published in 2017, although we were going for quite some time before then. And we're now in the 5th volume of monthly issues. And each monthly issue comes somewhere between 40 and 50 pages, and that's one item to a page of information. And we distill down a lot of complexity so decision makers can access a huge amount of complexity very quickly. So next slide, please, Mike. And this is what some of our journals look like. There's a range of ordinary editions and special editions there. We operate as a subscription model, so we don't take advertising. We're quite fiercely independent. We don't like to sort of toe anybody's line. So what you'll hear from us is our own personal views, not tainted, not influenced by anybody other than our own views of what we think is as close to the truth as we can get. And we cover technology and commercial activity around the world. And the idea is we take apart what's happening both on the commercial side and the technical side, and we just translate it in plain English. And you'll see from that slide there, we do things like we can extract out from the work we've done special editions around space. We've had demand for special edition around what's happening in China. The Graphene Gateway cover there you see was the one that Mike and I talked to in the States. And next slide, please, Mike. And this is some of our activity so far. And the Nixene Journal has contributed to this 2018 report to Congress, the US-China Economic and Security Review. So one of our guys, Rob Wielden, was asked to prepare an overview of graphene in China for this report, and he led the activity there. This year, we've been commissioned to create a briefing report to the US government for graphene manufacture, looking at sheet graphene manufacture. We'll come talk more about that later, looking at the economic impacts and what technical activity is going to be expected over the next 5 to 10 years. NASA have also asked us to deliver an interactive briefing. Yes, NASA knocked and came to our door, which was quite surprising and flattering, really. So we're delivering a special event for them, an interactive briefing where the rocket scientists get to grill us about the use of graphene, particularly with the space application. And interestingly, we've been asked specifically to reference the space elevator, so we'll be getting grilled on that. We're not going to cover the space elevator much in this presentation, but if any of you have questions about it, happy to take them. So
yeah, and we wanted to point out with this, didn't we, Adrian, that we are very close to sort of US government Congress and the parliamentary action committees, and hence, and now as a UK companies, we are now seen to be the lead and one of the leads in the graphene environments globally.
yes, and we think that's because we just major on independence. Thank you. So moving on then to just looking at the science and manufacturing state of the art. I've got a huge amount of slides. I'll get through them fairly quickly, but you're a smart bunch of people in the audience, so you'll be able to keep up. And if you want to keep copies of the slides, they're available after this presentation. Just ask Steve, you'll get a PDF of these. So graphene is carbon, nothing else. That's it, pure carbon. And you're all aware, it just looks like chicken wire. So this model here just shows graphene atoms in the hexagonal lattice all connected up together, sp2 hybridized carbon for the chemists in the audience. Great, thank you, Mike. And most of you will have probably heard that graphene is a Nobel Prize winning material, and André Costier first isolated graphene at the University of Manchester back in 2004, so just short of 17 years ago. And everybody probably knows the story of the sticky tape, where they took a piece of graphite, put some sticky tape on, and then peeled it off, stuck sticky tape back on, and kept repeating that. And it was a bit like splitting a deck of playing cards. Each time you put the sticky tape on, you're splitting the deck in half and more, until finally you get down, you just one atom thick layer of graphene is left. And everybody thinks they won the Nobel Prize for mucking about with sticky tape. Partly, that's the story, but the really important thing behind the scenes is what Costier and André did was once they isolated graphene, first of all, they proved it was a one atom thick layer. Then they prodded and poked it with expensive toys, electron microscopes, Raman spectrometers, and proved they got what they said they had. But more fundamentally, and this is something you need to get your head around, before 2004, graphene was considered impossible to exist. So it was written into textbooks that 2D materials would either curl up or just evaporate. They were completely unstable. And so what André and Costier were doing was actually tackling something which was thought to be impossible, and they succeeded. And now there's a whole host of 2D materials which have been discovered. More of that in a minute or two. So there's a lot more behind that Nobel Prize in Physics than meets the eye. Andre's still working in the UK at the University of Manchester, and he's based just around the corner from the National Graphene Institute, and I think he works a couple of floors below Brian Cox. So on to the next slide, please, Mike. Now, you'll hear a lot about 2D materials, so we just want to talk about this. Now, graphene is that flat piece of molecular chicken wire, and everybody thinks it's just called 2D because it's flat and thin. Well, actually, it's not quite 2D because the atoms actually have a height in the Z direction, as well as dimensions in the X and the Y. It's 0.3 of a nanometer, but it's still got a height there. So it's not, you could argue, it's not truly a 2D material. The original reason that graphene was called a 2D material is because the mathematics that describes the way electrons flow across that sheet can be described without the need for a third dimension. So that was the original reason they were called 2D. Now we finesse that a little bit more, and there seems to be general agreement amongst the scientists that the dimensions describe the number of dimensions a material can grow in and still remain the same material. So everything you're looking at on this screen is just pure carbon. It's just arranged in a different form. So we've got fullerenes. You may have heard of Buckminster fullerene or buckyballs at the top left. That's C60, that particular one, discovered by Harry Kroto at Sussex University back in the 80s. And that is a ball, just like a soccer ball, made up of hexagons and pentagons, 60 atoms of carbon there. And you'll see that you can't add any more carbons to it without changing what the nature of the material is. So it can't grow out in any other dimension. So it's a zero-dimensional material. Similarly, cyclocarbon below it, that's 18 carbons in a ring, alternating single, triple bonds. This was just discovered probably 18 months ago in Switzerland by researchers at IBM. That's another form of carbon. Then we've got carbon nanotubes. These are basically like toilet rolls. So you can imagine just chicken wire wrapped up, and it can grow, the carbon can grow at either end in, let's say, just the X direction, but it can't grow out in the Y direction or the Z. So it's just a one-dimensional material. Graphene can only grow in the X and the Y, but not the Z. The way it grows in the Z is that you just stack more layers on, and the more and more layers you add on, eventually it becomes graphite. And then the other materials here, they're three-dimensional. So you can see the three-dimensional scaffold of carbon atoms in diamond and also amorphous carbon. And that can grow out in the X, the Y, and the Z. So hopefully that gives you an idea about what we mean when we talk about dimensions. So it's, if you like, the degrees of freedom that the material can grow in and still remain the same material. So next slide, Mike. Andre and Costier, if you ask them quietly, probably think that the actual second paper they published is probably more worthy of a Nobel Prize than the first one. Maybe they should have won 2 Nobel Prizes, because this what they discovered was there's a whole landscape of 2D materials out there. It's not just graphene. So we're not going to go into this too much in this talk, although we could spend a whole hour just more talking about this. There are thousands of potential 2D materials out there, and they can be layered up either on top of themselves in a homostructure, like graphene layered on the graphene eventually becomes graphite, but then you could layer up materials with different properties. So you might have hexagonal boron nitride on top of graphene and any mix and match you care to name. So you can see that with thousands of potential materials and infinite number of ways that they can be combined, you have a massive potential for designer materials of the future. And these things are called van der Waals heterostructures because the layers are held together with van der Waals bonds. Just one example of one of the things you might do with this, you could layer up some of these heterostructures. Researchers have already created a material which acts like a diode, a light emitting diode, but you can change the color of the diode by altering the voltage that goes across it. So the color of the light that comes out can be altered. But that's a whole other conversation that we could have, and this is going to keep researchers engaged probably for at least the next generation of scientists and more. So next slide, please, Mike. Graphene, you'll have all heard, 200 times stronger than steel, probably the world's best conductor of electricity, and it's almost the world's best conductor of heat, although another one of these two-dimensional materials, hexagonal boron nitride, that's what the HBN stands for there, is actually a better conductor of heat. It's flexible, transparent, it's got the highest melting point of any material in a vacuum, so you need to take this up to 5,500 degrees centigrade before it will melt. And in fact, graphene doesn't melt, it's sublime, so it goes straight from a solid to a gas. But this material could probably sit on the surface of the sun and still be recognizably graphene. It's very stable material, and it's also non-toxic, so it's not going to kill you, which is one of the attractions for me working in this field as well. It's very tear resistant, and these two ones on the bottom, the world's most impermeable material, the world's most fatigue material, these were just discovered last year, so these are just months old. And Mike, you're just as astonished as I am about the pace with which even the research is moving, let alone the commercial stuff.
No, it's incredible, and another interesting point I always find is in terms of the electrical and thermal, properties of the materials, the HBN and other sorts of graphene. The interesting fact that it only conducts across the X and Y axis and not Z. So there's a massive use for this material when we start working it forward. And if you look in terms of I believe it's HBN, isn't it? It's Adrian. In terms of it's 10,000 times less conductive in the Z direction for electricity.
That was graphene, Mike. Yeah.
Graphene,
so,
sorry.
Yeah, 10,000 times less electrically conductive vertically than it is horizontally. Yes, quite right.
Which, in terms of the applications for that, are limitless.
Yeah, exactly. The world's most fatigue-resistant material. It'll take a billion cycles of stress before it breaks. And the world's most impermeable material, 1 atom thin of graphene. This was discovered by researchers in Manchester, again, Andre Geim's team. They've discovered that 1 atom thin of graphene is equivalent to a kilometre thick wall of glass when it comes to holding in helium. You just got to think about that, it's mind-boggling. Again, I could talk for hours on this slide, Mike, we better move on. So with all those superlative material properties and the Nobel Prize being awarded, interest in graphene shot through the roof just after the 2010s. And everybody expected graphene to be rolling off the production line on the scale of rugs and carpets and do massive, wonderful things. Then they got black powders, and which was the current state of the art. And everybody went, oh, is that it? And then even worse, when people started to add these black powders in polymer composites and various other things, they found it made matters worse. The performance actually got worse by adding graphene to it. So it got a bad name, and there was a reaction against the hype, this trough of disillusionment. Then along came sheet graphene started to be made, and this is where you actually lay down a single atomic layer of graphene on copper and other metals. But the problem was it was still stuck on the copper foil, very difficult to get off. And so again, expectations were raised and down it came. Now what we're beginning to see are real applications coming through, and Mike is going to talk about those just after I finish talking through some of the science bit. So be aware of the hype, and be aware that you're probably coming at this from people telling you, oh, that graphene stuff is all about hype. It's never going to amount to anything. Real stuff, exciting stuff is happening already. And this is graphene powder and sheets. You can see here on the left-hand side the powders, on the right-hand side the sheet. I'll come back to that a little bit more, but defect-free graphene is the ideal. And remember the term single crystal graphene, because that's going to become increasingly important over the next few years. Next slide, Mike. Just quickly how graphene's made. So graphene is made from graphite. Graphene is to graphite as a single card is to a deck of cards. And so you can basically you tear graphite apart and break it down into these single layers, and that's how you get graphene out. The definition with the Royal Society of Chemistry between the boundary between graphene and graphite is 10 layers of graphene, and then it's called graphite. But that's for electrical purposes, for electronics applications. It's a little bit more nuanced than that when we come to things like composites, but we'll talk about it later, perhaps in a quick Q&A. So, when
we're in DC as well, there was a huge debate and quite animated debate over, you know, what was graphene and what is graphite, wasn't there?
Yeah.
And in some, it's interesting. We've been talking to a number of companies in many ways who said, you know, you define it as that, but even if it's 15 layers, it doesn't matter if you're getting a 50% or 40% improvement. So it's quite interesting debate.
Yes. Yeah, don't get hung up on the definitions. If it does what you want it to and it does it consistently and makes a big difference, then it's worth paying attention to. Great. Yes, moving on. Different ways of making it. You can, right at the very top, that blue line up there, that's called exfoliation. So you start off with graphite, pull it apart, and you, by mechanical, chemical, or electrical processes, you end up with graphene powders. You can take crop waste or biochar. This has just come out this past year. There are companies out there at the minute, and I assume that you can all see my video. This sample here is made by a company called Graphene CR. That's made from biochar, and that's graphene powder, and it's made by high temperature pyrolysis. So you can take food waste, crop waste, turn it into graphene. And then Mike, you familiar, you know James Tour, the guy at Rice University. He developed flash graphene, didn't he?
Yeah, oh yeah. So yeah, Professor James Tour from Rice University, Houston. I mean, a real character as well. But I think did he recently patent it last year? It basically moving recycling plastics back to carbon, and then we, you know, with the use of graphene, can put it back in. So basically, from a net zero or green perspective, you could start opening up landfill sites and also recycling plastics as never before. Yeah.
So yeah, take waste plastic, turn it into graphene. And there's a company called Universal Matter, which is, I think, in North America, which is going to be commercializing this. They've just they've come to an agreement with James to take on board the intellectual property and scale up. So we better move on. We could spend a long time.
And just when you get the slides, just on the bottom left, there's a reference to it if you want to follow through.
Very good point. Thanks, Mike. Yeah, all our slides have references where the sources come from. So I talked about sheet graphene being made on metal foil. So this is how it works. You basically get hot gas, methane, carbon with 4 hydrogens on it, get it very hot, bring it down to the surface of a metal like copper, which acts as a catalyst. The hydrogens pull off and come off as hydrogen gas. and then the carbon atoms land on the surface, and then they connect up in the lowest energy shape that they can, and that turns out to be graphene, this chicken wire. And then when the surface of the metal is covered, the reaction stops. And then you peel the graphene off or dissolve the copper away, and that leaves you with a 1 atom thick graphene sheet. And that's called the chemical vapor deposition method. And this is a way of making large scale sheets of graphene. Next one, Mike. There are some production issues with it. Basically, you get the graphene forming at multiple points, and then as these domains grow, they collide and don't quite connect up, and we get what's called polycrystalline graphene, which, can you move on to the next slide, Mike? And if you just click on that for me. And this is what it looks like. So what you're looking at here is a piece of copper foil with a 1 atom thin covering of graphene on it. And the amazing thing is, if you look closely, you can actually see that 1 atom thin layer of graphene. Can you see down the left-hand edge? There's that slightly darker strip. That's the blank copper foil. And then on the right-hand side, the larger area, it's got more of a silvery sheen to it. That's the 1 atom thin layer of graphene. You're actually seeing graphene. And graphene absorbs 2.3% of the light that shines on it, which is astonishing for a 1 atom thin layer. We'll come back to that later. So that's what the CVD sheet graphene looks like when it's made on copper foil. Next slide, please, Mike. And you mentioned, you recognize that the term polycrystalline now, and that piece of graphene that you saw on the copper foil was polycrystalline graphene, where the domains have grown together, and then you get these slight disconnects where they don't quite connect up properly, and these red lines on that image there show you where you get 5, 6, 7 and more membered rings. Now that's fine for quite a lot of applications, but for extreme applications, then we're after perfect single molecule of single crystal graphene, which is this chicken wire with no defects whatsoever. And that has already been made, and we'll talk about that in a minute. So next slide, please, Mike. So single crystal graphene. Crystal in this context means a repeating pattern. So you'll have in your minds something like a diamond or a piece of quartz or something which shatters when you drop it. That's not what we mean here by single crystal graphene. It means the material is made from a continuous repeating pattern of carbon bonds right through the material. And these bonds can bend and wiggle, and that's what makes the sheet flexible. So here I've just got a piece of cling film which shows you a visual illustration. But that's where we're headed. And single crystal graphene is the perfect material which will realize the immense properties of graphene. Next slide, please, Mike. And just to give you an idea about what polycrystalline graphene looks like at the moment, you can imagine this cling film with holes and tears in it and defects. And that's the current state of manufacturing. Now, I don't want to do the current state of manufacturing down, because that is still astonishing progress to make 1 atom thin material at industrial scale. This is good enough for electronics, but when we want to actually start to make take advantage of the immense strength of graphene, then perfect single crystal graphene is what we're after. And that's the longer term manufacturing challenge. Next slide, please, Mike.
And I have to add as well, the dark side of Adrian's personality, he actually likes the fact these are probably the world's most perfect knives if developed.
Maybe we'll talk about that a little bit later, Mike.
Yes.
So is it possible to make single crystal graphene? Yes. It means we're effectively making a single molecule, which is at the scale of centimeters, meters, kilometers. And when you think about it, that sounds bizarre, but that's what single crystal graphene means. A single molecule right across the whole surface of the material with no defects, nothing else. Next slide, please, Mike. And single crystal graphene has already been made. So we're talking about something which is now in the past. The Chinese at Peking University have made a single crystal of graphene, which is 50 mil wide, 500 mil long, half a meter long single molecule made already. Oak Ridge National Laboratory have also done work on this, and they've made single crystal graphene at scale already as well, on a similar scale. So the Chinese are way ahead of us. Interestingly, we haven't heard anything more from Peking University, have we, Mike, since they announced this?
Gone dark.
Yes, probably. Yeah. Right, next slide, please. So having said about making single molecules, is it possible to make graphene at industrial speeds? And remember, graphene is only 17 years ago. Before that, it was thought impossible that graphene could exist. So we just have a look at the next few slides, Mike. So this is a graphene machine. This is at the GEEC, the Graphene Engineering Innovation Centre in Manchester. This is called the Graphene Flagship. Have supported a machine called the Neutron, made by a company called Extron in Germany. And you can just see at the top of it, inside that cabinet, you might see a roller and a strip of copper coming down from it. And what's happening is, thanks Mike, and that copper foil is going down through a vertical tube furnace and then reeling up at the bottom underneath. And as it goes through the tube furnace, methane and argon, hydrogen, a few other gases are mixed in at high temperature, taken up to about 1,000 degrees. And that's a roll-to-roll process for making graphene already. And it can make 20,000 square meters of graphene per year. We don't know how fast it will go, but this machine already makes graphene. Next slide, please, Mike. This is in the States, a company called General Graphene. The machine there on the left-hand side is a similar reel-to-reel machine, but this time it's horizontal, and the grey bit in the middle is the furnace. The whole thing is about 14 meters long, which gives you an idea about the scale. Then they can make graphene on the copper foil, but then they've also got a graphene transfer line where they can take the graphene off the copper foil by a separate process and transfer it onto other substrates. And they've already got the capacity as of next month to make 100,000 square meters per year. And they're talking about having 1 million square meters per year capacity next year, 18 months. This is industrial scale manufacture by anybody's benchmark. Next slide, please, Mike. And this is General Graphene's process. These are the materials. Inside that red circle there, you can see we've got four little boxes. What you're looking at there is about a 300 millimeter square sheet. And on the far left, you're seeing just standard PET plastic, polyethylene terephthalate. Then the one next to it has got 1 layer of graphene on, the one next to it has got 5 layers, and the one next to it's got 10 layers of graphene. So they can already start to take off multiple layers, not just 1 layer of graphene, and start layering this up. Astonishing progress. And they've just come out of the dark project in the last 6 months. So we didn't know about this before the summer of last year. Next slide, please, Mike. And another company came out of the dark project in Korea, LG, you've all heard of. They've got a similar machine. This time it's similar to the Extron's machine, except it's wider, it's 400 mil wide. Just ignore most of the stuff on there, which is incredibly impressive. This is all Six Sigma stuff. They can make incredibly consistent quantities of graphene. But the thing I want you to take away from this slide is look at the speed. They can already make it at 60 meters an hour. That's a meter a minute. This is high speed production of graphene manufacture already. And what that tells us is this isn't even a thoroughly optimized process yet. There's a chance that we can go much, much faster. So not only can we make graphene on a large scale, it can also be made very, very high speed by continuous processes. This is industrial manufacture of graphene. Next slide, please, Mike. So we've gone from impossible to industrial in 17 years. Just recapping briefly, before 2004, this was thought to be impossible, these 2D materials. Nobel Prize got awarded, you've got the hype, everybody dives in and tries stuff, and then they suddenly realized that adding graphene into things like polymer composites made them worse. Interestingly, as Mike will tell you a little bit later, adding less is more. That's part of the secret that has been found. And Mike will talk to you about some of the companies that are playing with this. Then looking at sheet graphene, you can see that we can make it at industrial scales and speeds, and single molecules of graphene can now be grown at very, very large scales already. We're looking at industrial scales. This is within 17 years of it being discovered. I don't think any other material has probably got commercialized faster than this. So I'll pass over to Mike, and you can stop listening to my voice for a while now.
Thanks, Adrian. Okay, moving on to the commercial side. I'm conscious of time, so I'm going to rattle through this, and it's not because I want to give it any or show any less importance to this, but actually just by giving an overview, you'll realise the commercial activity that's going on, and now you've got a real strong understanding of the properties of graphene and the applications. And also here we've got obviously the commercial activities mostly around graphene powders, and then we've got the sheet graphene is starting to make appearance. On every slide, you'll see a little emblem at the top. So like top right hand here, where it's powder or whether it's sheet. So let's moving through that. So this is the first application. So a company called Innovate, they're making performance shoes, and they have something which is called the G grip, and it's across most of their range. So they put graphene into the soles, and through this, they have now started to improve the performance of athletes through grip, because it's a softer grip, but it doesn't wear. And interesting, they've had to reinforce the uppers with Kevlar because the uppers are wearing out before the soles are even starting to wear. And as you can see here, by adding graphene, it's 50% stronger, 50% more elastic, and then 50% more hard wearing. And on the left there, you've got graphene oxide powder, which they put into state before. It's polymerized. I always get that wrong, Adrian, with my teeth in. But yeah,
they put it into a dispersion, which makes it easier to mix in with the rubber and then polymerize it. Yes, you're quite right, Mike.
Okay, so here's a really good one, Perpetuous, which were a Wales-based or a Welsh-based company, so UK-based. So they were running tests with graphene enhanced tires and going through there. So the average of 40% increase in wear resistance over regular tires, improved rolling resistance. So as you see there, 30% improvement in fuel economy, and wet and ice braking distance were also improved by 40%. So basically you're creating a winter tire that can be used throughout the year. And interestingly enough, which is very frustrating, as we all know, in terms of the adoption in the UK, couldn't get any interest in the UK, got the interest in the US, and it's now gone out to the States, and it's being developed out there, all the IPs out there, which again is upsetting. And with those figures, why wouldn't it be adopted? Why wasn't this technology taken forward? But questions for another day. This is again really interesting. So company called Director Plus in Italy. So they developed basically an asphalt, and they placed a 1 kilometer stretch in Strada Provinciale in Aldintiene near Rome, and basically resurfaced the road with graphene. And you can see the figures there. So in terms of permanent plastic deformation, so i.e. the rutting value, so 30%, 35% lower rutting at a 60% improvement at the temperature range, so a 35% sorry, rutting improvement. And then major improvements to the surface life and fatigue resistance improvement measured over 250%, which is incredible. And the one thing about adoption, which is great on this one, is the fact that Curbridge in Oxford, so the Oxfordshire Council have taken this on board and have got a test piece, and they've laid 750 meter test surface on graphene enhanced asphalt, and not sure about left and right, but actually going through the trial at the moment. Started in November 2019. We're not sure when this is going to actually land, and we started getting the figures, but at the moment I believe it's really looking positive. And again, graphene asphalt is on trial in Kent as well. So again, it at least there's a level of adoption, but you can imagine the impact in terms of the in terms of net zero and carbon reduction with the use of the tires, and also with the graphene enhanced asphalt service would be phenomenal. So at least some of our councils are starting to adopt this and trying to take it forward. Now, here's a friend of ours, Vivek. So he's got Space Blue working out of the University of Manchester, and we're working very closely with Vivek in terms of commercial and also in terms of the research. He's developed a mat, you can see on the bottom left-hand side is one of the first. So we all have a mat in our workshops and our home at the moment, which is a graphene enhanced mat, priced around £30. I'll give you that. The interesting thing is that the basic it's been recycled from tires, and the properties have improved dramatically with just the inclusion of graphene. You can see there top left in the old recycling how the rubber used to disintegrate and break up. This is now not happening, and so it's almost perfect. I think it is perfect in terms of almost classes of raw material from recycling. But I go through those figures in terms of the impact that could have again on the environment. Give you some rough figures. We've only got up to 2018, but the UK shipped to India 48,000 tons of tyres in 2013, and by 2018 we were sending 263,000 tons of tyres out to India. And internationally, At the moment, 2 million tons a year are dumped in Q8, and you actually see the space dump in from space. And it's not just tires as well. So we've got real issues, the recyclability of shoes, shoe waste, and also rubber gloves. So going back to innovate, if you can increase the life cycle of a particular product, then it could have a massive effect on the environment. So this is really great, and it's driving forward and is commercialized and is going from strength to strength. This one's really interesting. We when we're out in the States, we met with Debbie Molesky, who's global head of materials for Ford out of Detroit. I actually think she's been promoted now, Adrian, hasn't she?
Yeah, she's a technical fellow now.
Yeah, so she's come through. But interesting, they heard about graphene in Ford and the research side, and they basically got an intern and put them in the corner with some graphene powder and said, just play around with that. And after 3 months, they suddenly realized there was some real gain and something very interesting about the properties. So from 2019, they started putting graphene into the F-150 model, so continued graphene enhanced components, and it's in over 1 million cars. So you see there, so Ford found that less than 0.5% addition of graphene nanoplatement in a polyurethane foam gave an optimum result with noise reduction as well. So the real offspin of that, and the real surprise was, whilst they got the material properties 20%, heat endurance at 30% improvement, they actually got a noise reduction of 17%. And this is also, we found, will be very interesting to the aerospace industry. But what's Debbie's found as well, working and talking to her recently, is that because of COVID, people are starting to use their cars as offices more readily. So therefore, they're now using it, trying to move it into the cab and to try and create more silent vehicles for office use. Interesting. So British company back, so the Briggs Automotive Company, they basically put this into the outer shells, the carbon shells, and the graphene enhanced, so it's 30% stronger, or you can go 30% lighter, and is being trialed now and again, so pushing into the automotive industry. And it's great that it's seen as, whilst it's a unique and novel type of transport currently, we're getting some real results from that. And interesting, it was mentioned by, as Adrian mentioned earlier, about Stephen Fry. He really shouted about, and his words were, mark my words, graphene will change everything. So he's real advocate and bought into this. And I think it's going to be on the track next year, isn't it? We think, and
Yes.
Sorry, Adrian.
Oh yeah, yes, with Top Gear going around the track, I think next year or this year.
Yeah. Great. Okay. So this one, again, moving into a different environment, but really, if you say state-of-the-art mini labs, so field effect transistors. So basically, if you look at the transistors, the small circle in the center, you may be able to see some lines, but basically one chip can contain up to 15 conductors, and each conductor can carry out a different test. So blood tests, etc., and yes, can look to detect COVID. And at the moment, the company is called Qadir, and they're producing 9,000 of these for a day. So this means multiple results can be read out rapidly from one sample. So again, a really interesting and innovative piece of technology by the adoption of graphene. Now, the next one in terms of the field effect transistors, I'll let the chemist give you an overview on this one.
Basically, what's going on here is the black line that you can see on the diagram is the graphene, and then that's functionalized. So it has a receptive chemical group put on there. In this case, it's receptive to the SARS spike antibody, and then you set up the field effect transistor with a current, so with a voltage, so that the current is stable. And then when a sample is placed on the lab on the chip on the graphene, then if it doesn't contain anything that doesn't react with the functional groups, nothing happens. However, if you get spike antibody protein landing onto the functional group, that then causes a cascade down through the molecule into the graphene, and it changes the way that the graphene conducts electricity. And all of a sudden you'll see the current changing, and that can be picked up. Now, the sensitivity of this is astonishing, because this is work done in Korea. And Mike, if you just click again, you'll see that they can detect 1 femtogram. So there are 14 zeros before you get to the 1 of a gram per milliliter, which is astonishingly sensitive. I'll stop there, Mike, because I could talk about this for ages.
Yeah, okay. And if you're okay, Adrian, I think we'll just rattle through the last number of slides and pick out a few just so we get time for Q&A, because I think that'll be more interesting. So we've got the Hall effect sensor, which is being developed by a company called Paragraph. They've developed that in the UK. So basically, in simple terms, they can basically take away the radiation hardened shielding, make these lighter and therefore more sensitive, and they're able to use them in space. We're going to hand this out, so it just gives you an overview, but the whole sensors are used in switches, shafts on cars, and they're incredibly sensitive. But basically, because of graphene, we've taken away the packaging that encapsulates the sensor, and therefore makes them lighter, smaller, and able to, again, to be used in space. Orbex launch vehicle, so due to be launched down in the UK in 2022, and basically it's a lightweighting piece. So the graphene enhanced side is actually the carbon composite body. And just interesting in terms of the two-stage rocket, they've been the exhaust systems have been 3D printed. This one's interesting, and anti-corrosion coatings. Again, working through. So basically, there's a test going on at the moment with two 300,000 ton ships. Now this has been done by Talga, which is an Australian company. And basically you can see there, so 7% greater adhesive for primers, so it bonds greater, 40% greater adhesion of subsequent anti-fouling coatings, and there's been a consistent improvement in abrasion resistance. And we were working with a company again, and out in the States with Allied Graphene Materials, and the US Navy were incredibly interested in their paints, graphene enhanced paints. And this again could be transformational for the world in terms of how steel is used in the anti-corrosion properties. And again, for the performance of ships where they haven't got tons of paint, and having to bring them and pull them out of service just to completely protect them. This one really interests me in terms of sort of the planet, and basically 21st Century Convention Center, hotel and road in Yucatan in Mexico. So basically this is another one in terms of the frustration of adoption, but it's graphene enhanced concrete. So with a 0.03% graphene oxide by weight, increased sort of the strength of concrete by at least 25%. And we say at least because there's some production issues at the moment where there's no uniformity in production. And actually, so when we say it's at least 25%, when that's slightly refined, it will improve. But again, no adoption by UK and the government. And you look there, if it was adopted globally, it wouldn't take 2% as a minimum off of global CO2 emissions immediately. You don't have to change any of the process, don't have to change any of the systems, but obviously there's some resistance to it because it's transformational and it could take it 25% out of production. And again, just on the right, you can see those figures in terms of globally current cement production accounts for 8% of the CO2 emissions. If we could bring it down to 2% saving immediately. And Adrian, do you want to explain the chart on the left?
Yeah, just very quickly, this is a review of literature done with putting graphene and graphene oxide in concrete. So this is raw data that you're seeing. The variability of those yellow lines, you're seeing different graphenes with the horizontal bars, and then the compressive strength improvement along the bottom. And you'll see that some of these are approaching 45 to 50% improvement in strength. There's a lot of variability between the different tests at the minute. That's probably, we think, because it's the way the graphene powders and dispersions are mixed with the concrete. There's a lot more work that's been done actually in the last few months on this, so that people are getting very familiar with this. We're seeing figures of 35% improvement coming out consistently already. So this is ripe for adoption, like Mike says. There's just an inertia in the industry to take this on at the moment.
Yeah, and also with it, there's also a decrease in porosity. So when they were originally going to build, it was for a seawall, and actually they were so amazed by the properties and even the flow properties and cure properties that they actually decided to build everything with it. And again, from the UK, we need the UK government to get involved and then drive certification and testing to drive this out globally.
Yeah, and the porosity was important, Mike, because you don't want salt water penetrating the concrete and corroding the rebars inside the concrete. Graphene stops that.
Yeah. Okay, Adrian, on this one.
Sure, yeah. So we've gone from impossible to industrial in 17 years. The summary really is, you think graphene is overhyped, I hope we've made you think again. As Mike was saying, we're seeing double-digit performance improvements. This is unheard of. Normally, you're seeing sort of fractions of a percentage improvement, and that's with multiple applications using graphene powders and dispersions. We're also seeing CVD graphene. This is the sheet graphene starting to make an appearance in the sensors, and you can see what it does with those field effect transistors and the Hall sensors. There's lots of other applications starting to emerge. Graphene can do all sorts of things. It's a Swiss Army knife. And as Mike showed you from the Ford experience, you think you might be getting all the benefits by, let's say, adding graphene to a polymer composite to get heat resistance improvement, strength improvement. But accidentally, there are other benefits that emerge as well, like noise reduction, which was a complete surprise. So if you're in the field of playing with graphene, and you're mucking about with this stuff, then look for the unexpected benefits, because you might find graphene is doing a lot more than you realise, and there may be an even bigger benefit lurking in your data that you might miss if you didn't look for it.
And then final word, the big frustration is this grew out of the UK. It's a UK technology. We led the world in it, and because of the hype curve and issues, we are still the academic lead. But again, as usual, we are the poor commercial partner in terms of the adoption of this technology, and it's all going offshore. So I'll leave it at that, and that's the end of our presentation. Thank you very much, everybody.
Excellent. Well, thanks, Mike. Thanks, Adrian. I think it was very enlightening. I think you're quite right. There has been a lot of hype about graphene, but I hope you've just demonstrated that it's all justified. So I'd like to now kind of throw it open to the attendees, really. If you've got any questions, please post them in the chat box to everyone, and we'll work through them. But maybe I've got one to kick off, guys. I think the benefits of graphene addition in various applications seem to be quite compelling, particularly the increase in wear resistance with tyres, the increase in strength with concrete, which in turn would reduce the usage of concrete. Does this kind of pose one of the questions for large-scale graphene adoption, in that the big corporates may be resisting it? Because imagine if you don't need to replace your tyres so often, then that's a big income stream gone for the tyre manufacturers, and likewise with concrete product suppliers.
Yes, Steve, you're absolutely spot on with that, and it is exact that point, and it's that balance between optimization, where you'll get a higher level of adoption, or disruption. And this is incredibly disruptive to a lot of industries, so like you said, to the tire industry, the building industry, etc. And I think that's where the issues are. So it's almost back to the debate with the sugar industries and the tobacco industries in the past. And that's why we think government needs to be involved to help to drive subsidy to help and support these companies to take it forward, or use legislation to drive it through. But again, we're trying to work it, and Adrian and I are, that the first adopters get the share of the market as well, if they want to look at the competitive side of things. You got anything to add to that, Adrian? Yeah,
just that you're quite right, Mike and Steve. You go to a concrete manufacturer and say, oh, we got this great product that you'll end up selling 25% less material. They're not actually going to welcome you in with open arms. However, there's a bigger game to be played with CO2 reduction, and if we can get political action to say, we'll subsidize the manufacture of this stuff if you can reduce your CO2 emissions and still keep the safety and the strength standard, then that's quite a compelling argument. There is another thing as well, that once architects start to realize the potential for creating lighter structures that are stronger, there will be a drive and a push from the designers of buildings as well to start to be more creative with graphene and concrete. So this change is coming. It's just a question of when, really, rather than if.
Okay. I've got a couple of participants who've got their hands up. I'm not sure. Are you able to post questions in the chat box, or do we seem to have a problem?
there might not be a chat box, Steve. So it might be that if we see people with their hands up, we can maybe unmute their microphones and get them to ask a question.
We can. I'm assuming everyone. I've put a note in the meeting chat in the conversation. I'm presuming everyone can see that, but maybe not. Maybe not. Okay. Well, let's see if I can. Just unmute those individuals. If that's okay, then the individuals with their hands up, I'll unmute you. We'll start with Emily Jeffries. You should be.
Emily's just muted there.
Hello, can you hear me?
Yeah, we can hear you, Emily.
Oh, brilliant! Thank you very much for the talk, guys. It's fascinating, so thank you. I'm one of the more naive people in the audience about graphene, so do excuse if this question is terrible. But my question is: can graphene itself store energy?
What a great question.
Yeah,
Adrian, that's yours, definitely.
That's a really hard question to answer. The way graphene transmits energy is, I'll show you. I've got a little model. It's through phonons. So it's this is where heat gets transferred through. So this is the lattice of graphene, and you can see you get ripples moving through it, and that's how energy in the form of heat gets transferred through. So I don't think you could easily use it to store and extract out huge amounts of energy that way. Similarly, if you put in electricity, it would tend to flow through and out the other side. So
but there is the factors in terms of the reduced resistance and therefore better use of power. So the effective use, isn't it?
Yeah, well, because graphene conducts electricity 6 times better than copper does, then you're going to get less losses of energy through due to resistance. So it's not a perfect answer to your question, Emily, because that's not naive. That's actually quite a deep question, and the answer is probably, I don't know. I'll have to think about that and come back to you a little bit more on that. But I don't think it's as straightforward as putting energy in, storing it, and taking it out. It'll be a little bit more subtle than that. I hope that sort of answers.
There's definitely some research going on in this area, Emily, but we haven't heard anything about it yet.
Okay, cool. Well, no, that's brilliant. I might ask you again in 6 months.
Well, actually, just one other thing, Emily. There is a technology called heat batteries, and if you have a look on our YouTube channel, if you go to Nixene Publishing into YouTube, you'll find quite a lot of videos there, and look for one called heat batteries. And basically, it's a way of storing heat in salt, so it drives off the moisture in the salt, and then the heat gets stored in the salt, and then to release the heat again, you just add the water back in again. Now, the role that graphene plays is that it stops the salt from re-agglomerating and keeps it dispersed, so you have a high surface area for heat storage. So graphene is sort of helping something else store heat and energy that way.
Okay, brilliant. Well, thank you very much, guys. It's been brilliant.
Thanks, Emily. Right, we'll move down the list. I'll just go down in order that I've got people on the list. Next one up is Paul Mesbris. Let me just, right, you should be able to unmute yourself now, Paul.
Are you there, Paul? Oh, you've just gone back on mute.
Can you hear me?
Yes, got you now, Paul.
Oh, great. Well, thank you for the presentation. It was very good. Based on my research, I found that the 3 criteria for sort of commercial adoption are price, scale, and repeatability. And I wanted to see if you sort of share those sort of parameters, what sort of pricing you might want to see from manufacturers down the road in order for that to be achieved on whatever metric you want, kilogram, ton. And if you've heard about a company called NanoExplore based in Canada.
Yeah, we know about NanoExplore. They've been going for quite some time, actually, probably about 10 years. They're a good company. I think they're playing around. Yeah. Go on, Mike.
No, I was going to say, Paul, no, that, yeah, I'd agree with all your points there. And it's always a challenge in adoption. You probably know that. One of the things that is quite interesting when started doing the research with graphene is the fact that where a lot of the failures occurred, and I don't know where you operate, Paul, but you'll have found that people were just throwing a large amount of graphene into experiments and it was failing. And as you've probably seen from our presentation, when you're putting 0.03% of volume in, etc., then they started to make the gains. So people have the feeling that graphene is incredibly expensive, a raw product, but however, and there are some volume issues in production, but you're using so little in the production process to get the gains of 30–40%, then it becomes incredibly viable. I don't know what you want to add to that, Adrian?
Yeah, I do. When graphene first started to come out, probably about 10 years ago or so, then companies were selling graphene around about tens of thousands of pounds or dollars a kilogram. Now it's being made for very low hundreds of dollars a kilogram. So the price has come down by orders of magnitude. And also in that same period, some companies, particularly First Graphene, they've really got to grips with Six Sigma principles on their production processes. They've got very consistent production sorted out, as have quite a lot of other companies as well. So we're starting to see real professionalization, solid supply chain thinking, and so you're getting lower consistent prices with consistent quality for assured standards.
Thank you so much.
Thank you, Paul.
Yeah, thanks, Paul. Right, we'll move on. Russell Crowe, you should be able to unmute yourself, I think.
Yeah, I'll give it a go. Can you hear me?
Yep.
Yes, we can hear you, Russ.
Brilliant. Okay. Thanks. Well, I think Paul kind of stole my question, so I'll ask another one instead. In terms of the amount of energy that you have to put into the current production processes in order to extract graphene, when you're looking at sort of end-to-end carbon footprint, is it still delivering benefits, or is it consuming more energy in carbon that it's saving in the end application?
Can I take that one, Mike?
Yeah, go on. I know Russ very well, so I'd rather not answer. He'll come back at me.
It's all right. Oh, do you want to answer this one then?
No.
Okay, right. So for things like this CVD graphene, then you're making that around about 1,000 degrees centigrade. So the carbon footprint of that is going to be challenged right from the word go. But you'll remember that I talked about making graphene from biochar, and that material there, because it's made from biochar, it's actually the energy you put in, you still take it up to a high temperature, but the numbers have been run on this stuff, and it's actually carbon negative in terms of its manufacture and transport to point of use. So you're actually, by making this stuff, you're actually taking carbon out. It's carbon dioxide.
And it also brings in, Russ, in terms of the sustainability question, which is always the challenge for commercialization. You know, that the life of the product now is increased, and therefore you're getting the reduction of the footprint through that, and then the less recyclability, etc.
Excellent stuff. Thank you.
Okay, thanks, Russell. Right, next one, Neil Human. You should be able to unmute yourself, Neil. Neil?
Still on mute currently.
Okay, maybe he's new to it. We'll move on then. John Whiting, you've got a question. You should be able to unmute yourself.
Yeah, can you hear me?
Yes, can hear you, John.
Okay, good afternoon, good evening. I'm a mechanical engineer, and I'm just trying to conceive, if you can outline, this material which is portrayed as various forms of dimensionally various forms. When it comes to using it in road surfaces and tyres and on the hulls of ships, etc., is it still in a discrete layer form in the road? So take the road as an example, or is it small, tiny nano sheets, I suppose you'd call them, you know, that is added to it? How does that work?
Adrian?
Okay, I'll talk about this one. Yeah, you're quite right. Nano sheets is probably the best way of describing it. So again, you're talking, particularly when you talk about roads or polymer composites with the powders, these powders here have tiny nanoscale pieces of graphene, and what they do is that they operate down at the nanoscale, and they join up. Let's say it's asphalt, so this will actually go into an ingredient in the asphalt called I think it's called a polymer modified bitumen, where it's basically a plastic that's put into the bitumen for hard wearing surfaces. And what the graphene does, it connects up parts of the polymer chains on either side, and then acts as a bridge, and it can flex and it can bend and it can transfer heat quite efficiently between. So it forms like a composite framework. Does that help you understand that? So it's not a continuous one atomic layer running through the whole road, if you like. It's lots of.
Well, it couldn't be, could it? No, exactly. Yeah. So yeah, thanks. That does help. Yeah.
It is, and I'm glad you asked that particular question, because people do get this confused. They think that, you know, if painting it on the side of a ship, for example, it's a continuous piece of graphene running all the way along. But it's not quite that at the moment.
No. Okay, thanks.
Yeah, it's a good question.
Okay, yeah, thanks, John. Neil Human, are you still with us? If so, would you like to unmute yourself and ask your question? No, you must have disappeared. We'll move on. Tanya, you should be able to unmute yourself.
Yeah, Tanya was unmuted a second ago.
She's on mute at the moment. Tanya? Hello?
Oh, can you hear me now?
Yes.
Yeah.
Oh, okay. Hi, I'm so sorry. I loved the presentation, and it's just been such an eye-opener. I think I was one of the engineers who heard about graphene a few years ago, and like you said, there was so many problems with it, and I thought it was kind of just dismissed it and thought not much else of it. But I've always understood some of the, obviously not the technical side, but the practical uses for graphene. But I work in a factory in India, and we make instruments for aerospace for measuring things. And I've always and we're looking for new things. But I wondered, I mean, in terms of adopting graphene into industry now, is it? I mean, you're saying that it's available. Is it available on the open market, or is it patented, or do you have to have a license or something, or is it available? Is it something that you can actually buy and try and use and knock around in a laboratory or something? Or?
No, yes, Tanya, it is absolutely available, and I think a first graphene, so the biggest producers currently, Adrian.
They're one of the biggest, yes. There's quite a lot of graphene companies, probably a few hundred out there, of which probably maybe about 20 or 30 are at the top of that pile.
No, we had that with Professor James Torwer in the States. He said, you know, you can only get all the kilograms, and the team said, well, I can send you half a ton if you wish. So even James, working in that environment and experimenting, was only able to, or thought he could only get kilograms.
Yeah. Okay. So it's a case of just going to a private company and just asking for some graphene, I guess.
Yeah. Sorry, go on, Adrian.
Yeah, sorry, Mike. I would ask questions about the consistency of supply. So just make sure that, as well as the price, you're looking for sort of their quality control procedures, the usual sort of things to make sure that you're getting good material. That will sort the wheat from the chaff. The other test you could apply to a graphene supply company is to ask them if they're REACH registered. That's REACH, and the REACH registration applies in Europe, and it's a relatively expensive process to get REACH registered, but it's a guarantee that the company has jumped through all the regulatory hoops and hurdles. So it's a good sort of test to see if they're one of the top companies in the world, if that helps.
Yeah, it's great. Yeah, it would just be interesting to experiment. Oh, sorry to interrupt.
And do play with this stuff, because this is evolving science and technology right now. There's a very good chance if you play with it and put it into things, you might find something that nobody else has found, and there's there's plenty of fertile discoveries to be had yet.
Yeah,
And,
fabulous.
and to drive progression further forward, Tanya, if you want to drop Steve or the IMechE an email, we could recommend a few people or suppliers just to get you started. And again, if you wanted a separate conversation, please let us know.
And we can also put you into the people at the Geek.
Yes.
Yeah, thank you. I appreciate that. So just what a great seminar. So thank you both so much, and thank you to IMechE as well. Yeah, brilliant.
Okay, thank you, Tanya. Okay, Neil Human, are you back with us? If so, would you like to unmute and ask your question? No?
We're still struggling with this technology.
We are.
Yeah.
Okay, any more questions from anybody? If they'd like to click on the raise hand logo.
Yeah, there's
Sorry?
Neil, he's waving, just in an image a second ago. There's Neil, yeah.
He can't unmute.
Yeah, sorry, Neil.
You can try through. You can try doing mime, Neil.
I've given him permission to unmute, so you clicked your little microphone button, Neil. Or do you have a? Should we move on? Okay. Oh dear, he's gone again. Right. We've got Bill Brown now has got a question. Bill, you should be able to unmute yourself.
Yes, can you hear me?
Yes, I can hear you, Bill.
So I'm a mechanical engineer as well. Thank you. Great presentation. Thank you. What I'd just like to ask about we've used, been in the chemical industry quite a bit of my life, and we've used graphite heat exchangers quite a bit. They've obviously got trouble with the mechanical properties, but they're very, very good heat transfer. You haven't talked very much about heat transfer applications for graphene. Could you just, have you got any potential applications there?
Yes. Do you want me to take this, Mike?
Yes, it's fine.
So graphene can be used in a number of ways. It's being used to coat copper surfaces for heat exchangers and actually enhance the heat transfer with the metal by putting a very thermally conductive surface onto the copper. But also it's currently used in very high-end gaming chips. You know, these high-end computer processors for the advanced gaming machines. They're using graphene mixed in with polymer composites for the casing of the processing chips, because you've got to get the heat away because they work so fast. So it's being put into things like thermally conductive pastes and the chassis for mounting a lot of these electronics. And some of these, I can't remember the name of it now, something like a Graphene Dev or something like that. If you're interested, email me at the end and I'll get you a link. But this particular gaming chip, which was launched about 4 months ago, has become one of the top selling chipsets for high-end graphics for games. So it's being used in that end. For industrial applications in the chemical industry, that sort of thing, I'm not seeing too much in that area at the moment. We're still down at sort of very specialist areas. I do know that the space industry is looking at creating heat transfer pipes with graphene. So these are, if you can imagine a pipe which is sealed at both ends, and then it has ethanol inside, and you've got a hot end at one end and a cool end at the other. And the ethanol will migrate. Yeah, you're familiar with these things. Great. So
the copper tubes they've done that, but it's the same idea, yeah.
Right. Well, you can put graphene inside the wicking part of the tube, and that will actually improve the heat transfer of the graphene pipe. And there's been an example of that in the past few months that I've seen. Yeah.
And also the point that we mentioned earlier with Debbie at Ford, you know, they were really keen on that. And we've also had conversations with large aerospace OEMs who are interested in this and doing the research. But again, it's going to take 10 years really before that starts to come to the fore.
Yeah.
Has it put them into braking systems at all? Are you trying to get heat away from?
That's a question that neither Mike or I can't answer because we're covered by an NDA.
Yes.
Right. Okay.
We'll just smile.
Thank you very much.
Thank you, Bill.
Yeah, thanks, Bill. David Noon, you can unmute yourself.
Hello, guys. Can I say thank you very much for the presentation? Very informative. I've learnt a lot. My
Thanks,
question
David.
is, I'm a design mechanical engineer in the nuclear industry, and I was just thinking about the permeability qualities of graphene. So how does it stand up when I'm thinking of like rad hardening electrical equipment? Would graphene help us in that forum?
Yeah, shall I take that, Mike?
Yeah, is it in line with the whole sensors, etc., isn't it?
Exactly, yeah. So
Yeah.
graphene is being used, well, you know that graphite rods are used as moderators in nuclear reactors anyway. And layered graphene will work in a very similar way. But also when you get the single crystal graphene, if you start layering that up, then it will act in a very similar way to graphite, and it becomes a very effective electromagnetic shield. So EMI sources will be shielded, so you can get the wiggly bits of radiation will get stopped, but also it will the layers in the graphene will actually trap beta and alpha radiation as well. So yes, it could be used in shielding.
Oh,
but you'll
okay.
far more this than I will, because this is your meat and drink, all this industry stuff.
Yeah, we have a
Thank
lot
you
of
very much.
debates in the office, David, because two of our guys are ex-nuclear as well, so they're constantly talking about this.
Okay, thank you.
Thank you.
Yeah, but it's interesting. EMI shielding is an active area of research for making polymer composites with graphene in them, which have electromagnetic interference shielding already, and that's a particular area of interest for the space industry.
Especially the ECM countermeasures as well, isn't it?
Well, yes, of course, that too. Yes.
Yeah, is a big one.
Yeah.
Brilliant. Thank you. Thank you very much.
No, thank you, Dave. Any more questions then from anybody? No more hands raised at the moment. No. Shall we call it? Shall we wrap it up there then? As my stomach's starting to rumble anyway, so that's probably quite good timing. So yeah, well, thank you very much, Adrian, Mike. Extremely enlightening. Yes, I think you have convinced us that the hype is justified, or you've convinced me anyway. So yeah, I'd just like to say thanks again. Much appreciated. For those of you still online, if you'd like to email, if you'd like a copy of the presentation after, if you could email Nikki Baxter, who's our Yorkshire Region Administrator, at yorksadmin@imechenearyou.org, which is the email address you should have received the link from in the first place. She'll send you a copy of the presentation. We'll also get a link to the recording sorted out, and then if anybody wants to obviously have a link to the recording too, they can contact Nikki, or alternatively contact Mike or Adrian. Hopefully you made a note of their contact details when they were on screen, or Adrian and Mike, unless you want to quickly flash them up again before we sign off.
I think that might be a technical impossibility for me now, but yeah, give me a second.
Well, no worries if you can't.
No, it's not playing now.
Okay, no worries. Well, if you'd like to get in touch with Mike or Adrian directly, again, if you and you haven't made a note of their addresses, if you again contact Nikki Baxter, and she'll send you their email addresses. So, yes, thanks.